secrets that survive everything. So this talk is from two products exploitation chains that we found for scanning and applications. And we found a couple of exploitations that reported by bug bounty researchers. So this talk is about two exploitation chains and how to find credentials in runtime production applications. So I'm Hamad Gorzala, global pentest lead working in one of the Fortune 500 organizations. So I conduct penetration tests and review enterprise bug bounty programs. And I built a secret software. It's a tool to scan live applications traffic and find credentials. Because the patterns in this talk kept recurring all internet scale. So last year we received two bug bounty submissions. The first submission came in and the reporter identified credentials in JavaScript bundles, and he flagged the exporter. He stopped there and he did not proceed further. So a few months later, we received another submission. And this time the reporter again flagged the same pattern in the same JavaScript bundle on an entirely different application. And he did not investigate it further. So two submissions we reported over the last year course is we found credentials in JavaScript bundles. Nobody asked the question actually, what actually these credentials belong to. So I started reading the JavaScript bundle, not to read it as just looking for secrets, just to understand how to map that as the application, how it's designed in the application, how it functions. So with the four values that I found, I call the Azure AD token endpoint and the array account of the system or reachable just from the four values. So we're going to see exploitation 1 and exploitation 2 shortly. So exploitation 1. So the Azure AD chain. What four values if you find in the JavaScript bundle? What can you actually do with that? So you're going to see references to the portal. It's a dummy, intentionally built, purposefully built, vulnerable application just for the live demo. So if you see come across, it's just live, nothing, anything that you see, the credentials, data, it's completely it's fake. So this is the main.js file that gets shipped to every visitor of the application. So when you open an application, so you have to view the view source. That's where you can see the JavaScript files. So this is the main file, and you can start reading the file, and you see four Azure values. The Azure AD configuration values documented. So what actually these values are? So the tenant ID is the public identifier, which you would find in the login URLs that within the pod connects to the Azure AD. App ID is again a public identifier, so which is available, which is a resource identifier. Just in it's not like a real secret if exposed to on the JavaScript files or anywhere if you see it on the APIs. But the next one, app key, that's a secret. So that secret should never be exposed to front-end sources. If you see that anywhere, like an app key on the front-end JavaScript file or any API configuration, you see that, that's a secret. That's where that should live, right? So that should live in the backend. But with the four values that you were seeing here, app ID, app key, resource, and subscription key. So what is the resource key? So resource is like the identifier that tells what access it has, the token has access to. So it tells Azure AD that hey, I want access to this specific resource or an API. So subscription key. Subscription key is more like a key pass to pass through Azure API Management Gateway. So Azure API Management Gateway validates the subscription key before it has to pass down that request back to the backend API for validation. So for API Management Gateway to pass down the request, so it validates an active access token and also the subscription key. So with all these four values, what can you actually do? Anyone can actually do it. So let's see that. So this is the Azure AD APM architecture. So how an exploitation chain one has started. So the browser holds the JavaScript bundle. So just we have seen all the four values it has: app ID, app key, resource, and subscription key. That's all anyone. That's all anyone can do. They need it. So what I did, I started reading the JavaScript bundle. I started I crafted a request to call the Azure AD token endpoint, and with the app ID and app key. So once an Azure AD receives the specific request, so it validates whether the app ID and app key are real, right? It validates it, and then it generates an access token once the credentials are successful. So it generates an access token, and then I call the backend API. The backend API is called, the backend API I call for that specific service is to get the user information on the entire tenant, right? So I put together the subscription key and then the access token. I send back that request to backend API. API validated the subscription key and the access token, and then every account in the system was returned in the response. How was that possible? Because the access token that was generated, it's not a user token. It's a service principal token. So what's a service principal token? Service principal token is the app, it had highest number of permissions within the entire Azure directory. So it has the user impersonation level. No sign-in access is required. So with that access token and with the subscription key and all the 4 values that's available in the JavaScript file, we call the backend API and every account in the system official. So was authentication working correct as designed? Yes. Except that the service has to be calling from the backend. It's a service-to-service call. It's a server-to-server service call. Except that I call this token endpoint from the front end because the API, we have all the details and the API is still there. We call the backend API. So this is a standard documented walkthrough request where anyone having those 4 values can use it and plug in those values, and they will be able to get generating access to it. So let's see this on a dummy application now. So this is the portal that's built for live demo now. So it's all solid. So it's insecure shield portal, right? So it's all with it's also the view source. You can see the main.js file and the app.js file. The important thing for any pen tester is to read this through the main.js file to see what information it gives back. So just like I mentioned before, just not like looking for secrets or known details. Just read it as a map to understand what actually the application is giving you back, how it was built, right? So this is the Azure API configuration that we have just seen in. So it has all the details. So that's the Azure AD configuration subscription key, and I put in the log of secrets. So that's the Azure AD configuration that we have. So I took all these 4 values and then crafted a purpose-built request with it. So I pasted in all these 4 values and then generated an access token. So, and then I got the access token, I have the subscription key, and where to find the backend APIs. And luckily, it's the bad practice of developers writing the API configurations as well, exposing on the on the APIs. Sorry, on the JavaScript bundles itself. So I read carefully the JavaScript file again on a different JavaScript file. Now you can see what actually it can do. Like it has all the users, all the different API profiles, and documented within the JavaScript. So I call one specific interesting endpoint where it's called API/users. I send the request to the backend. So Azure AD validates these 2 values in here, and then immediately it returns back all the data that's relating to the entire tenant. Right. So it has over like 4,999 records overall. So every account in the system, you can see it has this password hash and solve that's written in the response. So I'm going to use this. So once I have this information, I put together a decryption kit just for the time being, just to save some time. So I use the decryption key just in here, and I crack the password and use that password to log into that particular user account. So every account in the system was reachable, so it returned almost an entire, all the details living inside the tag. Like I said, so this was purely because the access token generated, it has the super high-level permissions that has the super impersonation permissions, user-level impersonation permissions. So that's exploitation chain 1. And the next exploitation chain is pretty much the CryptoJS chain. So this actually is kind of creates a false sense of security because some developers thought that documenting the secrets inside the JavaScript bundle itself, they think it's a problem. So they have read almost articles, blog posts, and pretty much everything. So they realized, okay, I don't need to do that because it becomes riskier one day, right? So what they thought was they tried to encrypt the entire configuration object using CryptoJS encryption. And what it created is like a CryptoJS ciphertext blob storage that's sitting just inside the JavaScript bundle. Now, if the browser has to understand that, the browser can't understand it because it requires keys and it has to send to the backend server itself. Now, backend has to decrypt this entire configuration. So where does the actual key live? If the browser has to decrypt it, the key has to live in the browser. So how is it secure? Right? So it offers zero protection there. So there are 3 options by which the keys can be fetched by a browser. Is because the one, just like I mentioned, it has to the key has to live inside the JavaScript bundle itself, or the key has to be fetched from an independent API configuration, or the key must be fetched from one of the API decryption calls the app has to make. So these are the only possible ways that the browser can do it. And this is not safe because this is happening on the front end before authentication, and anybody can really capture the traffic and really see the data inside. So this is exactly what it looks like. So the CryptoJS encryption blob storage and the configuration, sorry, the decryption key just sitting 3 lines just below it, and the function that joins both the keys so that the browser can use to decrypt it. I'm going to go back again to the demo portal. So that's the CryptoJS encrypted blob storage, and then the decryption key, and then the function that joins them in the browser so that the browser can decrypt and understand it and construct the query to send it to the backend. Now, since I have all the details, so I just use the decryption key, put together a script so that I can immediately reverse it, and all 4 accounts are still reachable. I was able to retrieve all the Azure AD configuration back in response. So I didn't stop there. So I have the credentials now. That's what a pen tester or a bug bounty hunter or anybody, an attacker can do. They're not stopping there. Since they have it, they're going to look for more details, like to do more exploration of what they can find, right? So I use these details, and again I read the JavaScript file again, and got a generated token, and that token I used it back to the internal configuration that generated the database connections and credentials. Oops. There we go. So both exploitation chains. So especially this one is really, it creates a false sense of security because all secret scanners, they're regex-based patterns. They scan all the JavaScript bundles, API configurations, or APIs, headers, and lazy loader chunks and everything. This one gets skipped through because
it looks encrypted.
Based on the configuration they're encrypting, you are looking at like a big chunk of encrypted blob storage. The regex, you can create a specific regex for that specific pattern itself. So that creates a false sense of security, and most security tools miss this. So those are the 2 exploitation chains, and then so this is the decrypted dump that we have just seen, and the important thing, both applications had shift left security. So their source code repository is scanned by every single shift left scanner they had, the organization has. They had GitLeaks on every commit request, and they had SAS scanning on every pull request. But the credentials, all the credentials that we have seen, they went live. All scanners give a pass. How? Right? So this is, that's what we're going to look at in the next slides. So they have GitLeaks in CI/CD pipeline. The source code repositories scan for both entire two applications. GitLeaks said, okay, we're good to go. And then SAS scan happened, and then it gave a check mark, everything is good, and GitHub secret scanning, it runs an active pattern matching across the entire, based on the patterns, it scans all the repositories. It had all these shift left scannings in place, but that credential still went live. Nobody could explain it at the time, and we figured that out later. So where actually the gap lies, right? So if we take the current look at the stack, we have pre-deployment scans and post-deployment scans. So for the pre-deployment scans, industry has heavily invested into the pre-shift, shift left scanning. So we have GitLeaks, SAS, SonarQube, and other GitHub Advanced Secret Scanning, and they all scan the source code. So it scans what you commit. They don't scan what the application really serves. So if any secret is if any secret is committed by a developer into one of the source code repositories, this, the shift left scanning works just like an engine, and it flags it, so it stops the build, right? So all the pre-deployment scans works exactly as intended, as built, as it's designed, but once the pipeline has started, right? Once the shift left scanning has completed, the build pipeline works. So what happens? Shift left scanning completed, it gives a green check, and then pipeline runs. It creates a bundle, artifact. So what's an artifact? Artifact is just a JavaScript file you have just seen for the config for the application to function, right? So the build pipeline runs. It creates the artifact bundle, and then merges the bundle with the secrets. It bakes the secrets into the bundle, and then deploys that to the production artifact. So once it is done, once it's deployed, what do we have today in the shift right scanning is pretty much like vulnerability scanners. They look for injections, cross-site scriptings, headers, misconfigurations, everything. They're not pre-designed and built specifically for secret scanning. So the gap is between the pre-deployment and post-deployment, exactly that merge boundary. So if we take a look at this, developer writes the code, he commits the Git repository history, and then CI/CD pipeline scan checks in. So that's the last stage where it gets the automated coverage, scan coverage. Just like we just talked about, right? So once shift left scanning completes, the pipeline begins, the artifact is produced, credentials are baked into the bundle, and then the bundle is served. There is no coverage on that specific build between the build and deployment. That's the gap. That's the gap that we have today. So what are the 5 structural paths? So we have come across, and we have, I've read some more research articles, and this is what it comes down to: the 5 structural paths by which credentials are baked into production JavaScript bundles today, or AD configurations. So build-time environment injection, CI/CD pipeline variable substitutions, and lazy loaded chunks, SSR state serialization, and runtime configurations. So what are actually these? So these are exactly the configurations that happen once after a shift left scanning completes and exits. These are the 5 possible ways by which credentials reach JavaScript bundles to the production applications. So built-time environment injection is pretty much like a developer writes an environment variable. It stores a secret in the environment variable, environment file, and that environment file, he commits it to Git repository, the credential, the GitHub or the GitHub, the shift left scanners will catch it, and they will flag it. But what happens, how the credentials is getting bundled is because you are committing, so the developer writes that, stores the secret inside a stores the secret in an environment file. At build time, the Webpack define plugin will read the environment file and pre-bakes the real values into the combined JavaScript pipelines. That's how the credentials are baked, and that's how they're getting delivered to the Java, production applications. So these are all the 5 possible paths. So in 7 stages, how a secret gets escaped bypassing all the scanning layer and gets delivered to the final production application, right? Just take an example. Developer writes a secret into the Git environment. Developer writes a secret in the environment file. If the environment file gets committed to the source code repository, we have all the shift left scanning. Shift left scanning will capture that. So the build pipeline is blocked. So what they do, they git ignore the environment file, and then once they commit the placeholders to the GitHub repositories. So once the placeholder is committed to the Git repository, all the shift left scanners will inspect every single line of the code, and they will see the placeholder token. They will not see the real credentials, because credentials were not really committed to the source code repository. They're just the placeholder tokens inside it. Every scanner, once every scanner gives a clear check, the pipeline runs. So once the pipeline runs, the artifact is bundled. The pipeline builds the bundle and then makes the secret into the here in this stage 4. That's where the secrets get baked into, because that's where the define plugin will call the environment file and bakes the credential into that particular artifact and directly dumps that into the production application. So secret went from stage 1 to stage 7, escaping, bypassing every single scan. So if you take a look at this, two different paths. So the one path we have just seen is if the environment file gets committed, or if one of the configuration files get committed to Git repository, so the shift left scanning will be captured and it blocks the build. So these are the 5 structural paths that we have just seen. So these will not be captured, and they won't be captured by the secret scanners because it doesn't have an automatic coverage today. So looking at the landscape, so industry has invested so much in the shift left scanning, GitLeaks, secret scanning, Git Guardian, Sonar. They all well deserve the spot in there. On the right side, once the credential escapes and gets lived in the production application that it's getting served, so there is no scanner today that can really flag that particular kind of credential. So the runtime security gap on the right side, the shift right side, is almost nearly empty because there is no specific tool that's going to do it. So if we take a look example of how, we put together all the tools that we have. So we have repository scanners, we have shift right scanners, and TrupleHog has its own place, own layer of identifying the credentials, and it does live verification of credentials if it comes across, right? And the others are active crawlers, and the others there are new plays which run based on the template. They have huge number of templates, and they have almost 50 to 60 secret scanning templates inside as well. But they do not find all the API configurations. They do not scan the headers. They do not scan the specific JavaScript bundles, lazy loaded chunks, and the secrets in the HTML resources as well. They're solving a different problem that's specifically designed for something, but not for secret scanning. So Burp Suite has more plugins, and some of the plugins it has, it also, JS Miner, Sensitive Discoverer, TrupleHog, Burp extensions, they do have some sort of regex-based scanning. They will find some secrets, but no scanner is going to find you 100% of your credentials if it's exposed. So what actually the runtime secret scanner should have? So it should see all the 4 values. It should have all these 4 values. It should see what the attacker is supposed to. Sorry, it should see what the attacker is seeing. it should observe the traffic. It should capture all the XML content types, JSON content types, lazy loader chunks, and the SSR states, and pretty much the encrypted blob storage. And once the secret scanner starts scanning the JavaScript bundle or the production application itself, right? We know that the front-end application is completely of user identifiers. So there are public identifiers. They're intentionally put the public client IDs to be defined across all the JavaScript files, right? So without all these 4 values together, your scanner will either fire too many false positives, or it will miss completely what the scanner is serving, or sorry, what the application is serving. So 2 external researchers have, 2 independent studies show that the internet scale has not been scanned for secrets, right? This all happened in the last 6 months. These are the only 2 articles that I can find in the internet so far today. Because shift-right secret scanning is something new. Nobody knew the concept. Nobody believes that, the secrets really get committed to runtime, living in the production applications. So Intruder.io, they scanned about like 5 million application pages. They found 42,000 tokens. And Demir Nurullah, he's a Stanford University professor, so he published a paper on March 2026. They scanned 10 million pages, and they found 1,748 tokens, live tokens. So 84% of them living in JavaScript bundles, right? So this shows that, the all the internet scale is not scanned. This proves that, all the credentials, they reported the flagged credentials to the appropriate organizations respectfully, and most of them have remediated the findings they have captured. So attackers they always see the front end of your application. They will not see your source code. They will not have access to your source code. So all they will see is just the front end of your applications. So they already know this. If you want to start scanning your entire organization today for secrets, there is no answer to it. Because the current day dash scanners we have, they're not equipped with secret scan capabilities. They do not have that. So the runtime layer is the only layer the attacker always sees. That's where they start. That's where they always look, 24/7. They look at your applications. They see what, they will find they will read every single line of your JavaScript code. They will find credentials, they will find APIs, and once they find the exploitations, the change that we have seen, that's the result. So we're going to see this in a live demo portal application now. So this is the tool that I built. Get the target. So what it's going to do, right? So it will load the application in a Chromium browser, and it will start inspecting all the traffic. So it's gonna fire up the application in the Chrome browser. It's gonna inspect your traffic for JavaScript files. It will capture the API configurations, and it will find every single credential. It's gonna inspect every single line of code, and it will just find the credentials that's living in your API configurations or the JavaScript bundles. So I plugged in like 4 other tools just for comparison, so that we can see it. So Titus is one of the recent most open source security scanners. So it finds a few vulnerabilities. It's not going to find everything because it's missing secrets in the headers. It's missing secrets in the configurations. It's missing secrets in some of the regex-based patterns that it doesn't have with. So we have Trufflehog as an example here. So Trufflehog also does the live inspection. So it's going to look for the secrets it found. So that's the so far credentials it has found. So there's another BERT plugin it has. So it will find a few more. So this is not like, this is not a complete regex-based patterns. It will find sensitive information like, IP addresses or email addresses that's living within the application JavaScript bundles. So there is no one single application tool, the tool today that's going to scan for your credentials just like the shift left secret scanner does, because they are purpose built, and no purpose built today we have to scan specific assets for your enterprise organizations. So what's the remediation? Oops, go back again. Sorry. I can iterate to make it work. So that's the total overall numbers that we, within the scanner plugins that we put together using the Burp Suite extensions. So that's the comparison model of how it looks like. So what's the remediation for it? So the first two, backend for frontend, secret managers, saving your secrets in the Azure key vault, and then artifact scanning and the runtime secret scanning. That's the solution. Why? Because backend for frontend and secrets manager, number one and number two are going to remove your, those two are going to remove the credentials documenting in the frontend itself. Why? Because secret manager, saving your secrets in the secrets manager and have the application call the backend, BFF backend for frontend server, and at runtime, what it does is at runtime, application makes a call with the cookie. It's not going to use credentials anymore, because that's how the BFF pattern works. So your credentials will live on the server end on the secrets key vault, and then the application makes a call to the backend, and the backend uses the credentials, fetches the credentials runtime from the secret manager, and sends to the backend API to generate an access token, then send it to the frontend user. So there is no more secrets exposing, there's no more of maintaining secrets or getting secrets bundled into, on the front end. So if you compare the model, so before and after. So before the JavaScript files, the secrets are within the JavaScript bundles here. And after, the secrets are maintained at the key store. And then, when the browser makes a call, it makes a call to the backend API with the cookie. The cookie is only the sensitive, a client identifier that's going to send it to the backend user, the backend server, and the backend is going to make a call at runtime to fetch that credential and send it back to the backend API, generates an access token, and sends it back to the frontend user. So there is no way of exposing secrets throughout this traffic between the client and server communication. So what else can we do, right? Artifact scan. This is more, this is very underrated, and most security teams do not know this. Why? Because the scan at the front, the source code scanning, that's where every security team will look into, hey, my code is scanned, it's cleared. That's what they're going to look into and see. So once the artifacts are bundled, and then the artifacts is, that's where the artifact scanning layer has to be merged. And GitHub Advanced Secret Scanning, they also have this capability of doing artifact scanning, right? So the artifact scanning is the piece where it can find it can scan for the artifacts, that's getting bundled with the secrets. So the runtime secret scanning has to happen 24/7, because nobody knows, like, if I'm a developer, if I have an application, I'm making changes, I run the deployments 24 times a day. So something may go wrong all the time. So pen testers and application security teams, vulnerability management teams, they do this scanning all the time. They have to scan this all the time. So 3 layers of scanning: source code scanning, artifact scanning, and the runtime secret scanning. That will solve the problem of identifying credentials. Identifying credentials and getting those secrets fixed by the teams. So what's this for the application pen testers and bug bounty hunters, right? If they find a credential, do not stop at the credential. See what permissions it has, what it can lead, what it can give you access. Do you have like user access? Do you have like service principal access? And what can you further do? And important, responsible disclosure. If you find secrets, if you find credentials, if you find any specific information, responsible disclosure, or you can report to that problem teams. Because when the credentials are getting discovered or published to the on the live applications, today only 3 things are captured. 1, pen testers, 2, bug bounty researchers, and 3 attackers. 2 of them report, 1 doesn't. So this is the secret sifter tool that I built. It's completely open source if you want it. So you can just load it to the application. So it can scan up to 30 URLs or 50 URLs based on your machine size, hardware complexity it has. So it ships in different forms. So it ships in Burp Suite extension, it ships in browser extensions like Chrome and Firefox, and it ships in desktop applications, both Mac and OS. I'm still working on the MCP edition. It was halfway there. So you load targets into the target URL and scan the applications that it's going to find based on all the regex it has, and it has more capabilities of how you can load custom regex patterns so that you can find a custom credential that you're specifically looking for. Questions time.
Not a question, but I'm pretty shocked that modern day dash scanners can't find these secrets hiding.
Yeah. It's because they ever since from the beginning, they heavily invested into finding vulnerabilities.
Yeah.
They are you find injections, SQL injections, you find process tokens, they will find missing headers, they will look for secret, and they will look for session tokens. The shifter will never look for credentials. They're not designed for that. So there is there are a couple of companies that now making this as a profit. You know that? So there are more and more runtime secret scanning tools that's going to come up in the future. Because the industry is looking at it right now, and more runtime exploitations that we're seeing is based on credentials leakage.
Go ahead.
I think I got a little confused. So are you saying that the shift left scanners that are scanning for vulnerabilities, they're not looking to see if there's credentials in like the front end files, or is it like you're putting it in the environment variables, and then you're also I'm asking if it's the latter where it's like they are scanning for credentials, but they're not finding credentials because you put them in the environment variables,
Right.
and somehow the environment variables are leaking into the bundle of the artifact.
So
Or is it both?
No, it's the first one where they scan what you commit. You are not committing your environment variable, the environment files to source code repositories.
That's the developer 2-step.
Okay.
So that's what happens if you commit the environment file. Secret scanning tools, just like the shift left scanning tools, they will find it. The build is blocked.
Yeah. Okay.
So there is a different, there are different ways, like I said, 5 different mechanisms. There are environment files they can get ignored, but the frameworks that they're using, React, Angular, they are white, blue, they are all the frameworks they have specific documentation of how they're calling the prefixes. They have a prefix like, React_app. That means that's naming is the convention. When the build pipeline begins, the plugin automatically calls. It understands that, hey, it's a React_app. That means this variable has to live in the browser front.
Yeah, so then that's when the bundling happens.
Yes.
With the
So
video
it
or
all,
anything.
exactly.
Yeah.
It happens once after every scanning completes, exits the pipeline. That's when the artifact gets bundled.
Yeah.
So there is no scan happening between the build and the deploy. So that's the scanning layer, sorry, the gap. That's how the credentials are, baked into artifacts or configuration files and getting delivered to production applications.
And it seems like another part of the problem is culture. The security team should be reviewing the API's permissions to be least permissive, as well as looking at the main JS to make sure that these don't exist in that front end, which would be artifact scanning,
Yes, exactly.
but on the manual side.
Right.
Yeah, this is that. Wow. Okay. Now I'm scared. Thank you. Great prezzo.
Is this similar to how Claude Code's source code got leaked through an NPM package which didn't go detected through the CI/CD pipeline side?
Maybe somehow, but may not entirely be just because of this.
Threat actors doing source code exploitation though will stuff credentials in environment variable files and release them, so you can, if I can inject something through your NPM layer, I can have that code execute at build time, take secrets out of your environment, and dump them into the environment variables, and then get compiled in real time, hidden in your website as a way of exfiltrating secrets and tokens. It's pretty sophisticated. You're not going to see that as a normal attack pattern, but it's something that they can do. That environment variable file is miserable. Yeah.
So it's environment files, configuration files.
Yeah.
Anything that you do git ignore, that's how, because that's the documented layer.
Yeah.
That's how the document says, you
Yeah.
git ignore these files.
Yeah, I've seen people intentionally concatenate in environment variable files to create a secret that they've used to embed in there because it would bypass the scanners. It's like, are you my threat actor? Yeah.
So once I have found these credentials, I was working with a couple of developers as well to understand what exactly happened.
Yeah.
So they all give different reasons because it's one of all these reasons. So
Yeah.
deliberate scanner suppression that we see almost all the time. Scanners will find it and they will say it's a test token. So
Yeah. The what was that? Was it called?
backend for front-end pattern.
Is you're basically creating an API layer between the client side and the server side,
Exactly.
and it's all just cookie session, and then the back end, the true security token remains server side.
Yeah, everything is
Okay.
happening. The scanning with the fetching of the credentials and generating of the token is completely happening on the back end, so front-end users can never see it. And I've been working on a paper, research paper based on all of this. So you can find that in Zenodo. It's all about like how this is happening at an internal scale.
Yeah, this is really good.
Did you mention that like using something like Azure Key Vault could be used and then the front end just calls that and then it gets the secret in place?
Yeah.
Is that a relevant fix for this all?
So there are a couple of fixes, right?
Yeah.
So backend for front end and Azure Key Vault, both. That's one layer of like, how you can store secrets and fetch your secrets on the runtime.
Mm-hmm.
And the other layer is like, scanning your artifacts and 24/7 scanning your production applications if somehow something gets skipped through.
Yeah, I just know like I'm gonna go to an app team, if I find something like this, like, oh, we don't want to spin up an API server to handle all this, so having that key vault option
Yes.
is definitely something that they can work with and they're familiar with, so.
Exactly.
Is this somewhere like giving application role-based access, using something like that? Like I guess Lambda can do it, and some of the AWS serverless, I can give the application, either the Lambda function or the container, access to those specific secrets, make those calls, and then the back end, front end, yeah.
Yes, exactly, that's how
Yeah.
it should be done.
Yeah, and then it's credentialless. Yeah, 100%.
Yeah, the
Yeah.
reason all of these exploitations happen for the first one is pretty much because the service principal keys were exposed completely.
Yeah.
So that got elevated access to to me when I was doing it, and I was able to read every account in the system in an entire tenant. So when we worked with the specific provider, they said they couldn't find a way to see what and who uses those keys. So that's a gap as well, because if you're an enterprise company, global company, and if somehow your applications are exposing that.
Well, that's actually an interesting point too. What does your IDS IPS see when they see that? Yeah, those calls should have an origin,
Right.
and that back end front end should just reject anything that isn't coming through there. And then the gateway, like your Azure environment, should just say, no, I only trust
Yeah.
the BFF.
Because everything you expose now, it looks like your application, or any threat actor that working on that using that keys, it will
Yeah.
look like it's an application.
Yeah, yeah.
So they would
yeah.
not find what specific user
Yeah,
or
yeah.
who-
And that's what that session
Yes.
ID is supposed to, there the subscription, right? It's supposed to, that last step of, okay,
Yeah.
wow.
Because when we met, like I said, when we met with the provider, they said there is no way you can distinguish like who is logging in, who is accessing, and who is authenticating your system.
This has to be way deeper than, I mean, even those numbers that you posted, this has to be way deeper than that, just in the developers I've worked with.
Yeah.
Yeah. And it's not their, some of it is not their fault. They just don't know a better
Exactly.
pattern.
It's
So-
not their fault. It's
Yeah.
knowing and how the frameworks are working, because developers they see the documentation of GitLeaks
Yeah.
and they see how the documentation of React applications work or your White or Angular applications work. They do not understand that when you combine both together, what
Yeah.
the problem is going to create.
Yeah.
What's the black radius when someone finds it?
Yeah. Yeah, the impact side of that is huge. So,
Exactly.
yeah.
Any other questions? Thank you.